Back. Now we will see the input microwave network. Before starting that, we have seen that for a TM lines we can find the equivalent circuits, and for non-TM lines it's difficult to find the equivalent voltage and current, but it is not impossible, but it is complicated. So once we find that equivalent voltage and current, we can use the different parameters to study its property. Basically property in the sense between the port, whether voltage will be divided or will be like coupled, or it will be filtered or attenuated. So everything we can find out if I know the parameters between the ports. So for an n-port network, what is a port here is the way the microwave signal can enter or exist. If you, for example, for analogy, if you take a house, there is a 2 entry or 3 entry is possible, so 2-3 way we can enter and exit. So if it is a 2 entries there, it's called a 2 port. If it is a 3, it is a 3 port. So n port is arbitrary port. It can have a number of way input and output of a given network. So when you find the equivalent voltage and current, either for TM and mainly for TM, and non-TM is it is complicated, but it is not impossible. But once I know the equivalent voltage, that is what here it means for, I can use the circuit analysis techniques. So what are the different techniques in traditional electrical circuit analysis? We have Z parameters, Y parameters, and H parameter. Coming to the H parameter is mainly quite used in the transistor circuits to analyze that what is after writing equivalent circuit design, equivalent model, and find out what is the voltage and current of a circuit, what is the impedance, how much current is flowing it, and what is the gain. You know that gain of the any amplifier is related with the output by input voltage. And ABCD parameters, we will see it shortly after studying the S parameters. And ABCD parameters is also called a transmission matrix, and especially used for cascaded system. That is quite useful in a microwave network analysis, that we will see it after seeing that Z and Y parameter. That is a very short overview. We will see it because Z and Y parameter is not exactly or not in the syllabus, and also we are not much going to use it in the microwave network. But to bridge the gap, try to find out the relations between microwave parameters and Z and Y. We see that briefly. So here in each port, if I know voltage and current, I can write that matrix, Z parameter, Y parameter matrix, and I can find out what is the voltage will be in that other port. For each port, I have to know what is the voltage and current. At least if I, for example, if I take one port, let us take a second port. If I wants to know what is the voltage, current, I should know other ports voltage and current, and also I should know what is the Z parameters. Only I can find out unknown ports voltage and current if other information is available, or else I should know all the voltage and current basically to find out what is how much voltage is coming out, how much current is going out, or voltage is going out, that we can find out. So I should know that individual port voltage and current to find out power and transmitted power and everything. So it is very useful microwave input analysis. It will be very useful. Okay, so it will be very useful. We will use it in many scenarios in the microwave networks. We will see one by one, and in a maybe for a kind of analysis, I will tell some experiments, lab experiment, what we will do it in the microwave lab, and try to relate the things to theory. So of course you may have to see that radar networks and receiver transceiver based circuits. You will be seeing a lot kind of these devices. So where this parameter is immediately is going to be applied there. Okay, so this is a n port microwave network, arbitrary, and you have a port 1, 2. If you see that this is port 1, this is port 1, this is port 2, this is 3, 4, this is n port. So what you can see it here, so port 1, this is my incident voltage and current, V1 plus and I1 plus. Because why it's a plus? Because in nomenclature or notation, we always tell positive sign when there is an incident. When there is a negative, it's always reflected. The same principle we used in the transmission line. So here V1 is stands for the first port, what is the voltage incident, and first port, what is the current incident, that is I1 plus. So here reflected is the V1 minus. Only the change is the direction of the current. Always the current we will tell it is from right to left one direction, left to right one direction. So when the voltage current is reflected back, this is the opposite sign, that you have to keep it in mind. Similarly, you can see that here port 2 also similar, the incident and reflected. Here also there is incident and reflected, here incident reflected. Similarly for n port is incident and reflected. Now the thing is, why we need this Z and Y parameter is to link all these voltage and currents together in the one form. What is the form we use it here is because it's all our linear superimpositional equations, and all are linked together. So we can use that, all linear equations. If you're able to write in terms of linear equations, I can write into the matrix form. I think I've studied the classical mathematical, the solution for linear algebraic equations from matrix method. You are going, you can solve that. You can find x, y, z value. So similarly, we can write the matrix form of this voltage and current relating to the parameters. So here if you take the voltage and current, you can relate V equals to I into R. If you can see it here, you can see it here. This is V equals to Z into I. It's nothing but is Ohm's law. Instead of writing the single value, I'm going to write it in the matrix. That is only the difference. So it's quite easy to understand. So this is all voltages. This is all my impedance. This is all my current in each port. So V equals to I times R. R is here impedance, because it have a real and imaginary. So this can be a complex number. Okay, that you have to keep it in mind. This is not a resistance only the real value. It can have a reactance also. So it is a complex number. And similarly, compatriate part is Y parameters. So the same Ohm's law can be written as I equals to, I think you can easily write down this I equals to V divided by Z. So Z1 by Z I can write as a admittance. So same equations in the different form, I can write the current all ports, which is equals to the admittance matrix times of voltage in each port. Okay, that's a way quite easy to understand. So now this is what we use it in the circuit analysis, in the electrical circuit analysis. Parameters, what this called as a Z parameter, this is called as a Y parameter. So once I know that Z and Y parameter, I have a blueprint of the device. So I can immediately say that the quality, this is like a attribute of persons. Like if I know the Z parameter of the device or network or transmission waveguides, if I have a Z, these parameters, I can immediately understand what is the input, what is going to be output. That is what advantage of these parameters. So it's taken here quite, you can see here. This is Z14 is taken. It's nothing but if you take each element in the matrix, it is a voltage by current ratio. So what you have to do it in the matrix form as you have done in the algebraic, expand it. How to expand it? So I think you can understand here how to expand it. V1 in matrix, how you write algebraic equations. V1 equals to Z11 times of I1 plus Z12 into I2 plus Z13 into I3 plus etc. And so this is written in the linear algebraic equations, and in that you take only Z14. Okay, maybe for a simplicity, maybe I can use that some notes in that, so it will be quite easier, because if you look out n parameter n port, so it may looks like a bigger matrix, but actually it is very simple. So the two, if you start with the 2 port, you can easily understand to many port. I suggest you to read some simple problems and try to understand the concepts before going for equations and doing the derivations and problems. So why this we are studying this parameters? The main reason is to know what is the relation between output and input. Okay, and see simple different types of problems, so you can easily understand the necessity of this different parameters. So for simplicity, maybe this is too big colors, so I can take some color. So this is a 2 port. For simplicity, I'll take a 2 port device. So let us take simple 2 port device. This is, it will have a 2 lines. This is quite different. It's what you normally see it in the low frequency circuits. If you take an input, normally it is only 1 pin will be there. Why we need 2 pins? Okay, there are 2 pins in the input. This pair we call as the 1 port. Again, output pair of terminals we call as a 1 port. Okay, why there is a 2 pins? Okay, so this is a reason we will come with a high frequency, because when you say that high frequency circuits or devices or transmission lines, as we have seen that earlier, but high frequency, it's nothing but C by lambda. When you are going with the higher and higher frequency, the wavelength of the signal is coming, operating wavelength of the signal coming to very smaller and smaller. It is comparable to the physical length of the line. So what happens, the voltage changes instantaneously, so that if the impedance is not matched, the wave we have seen in the transmission line, it will have a distributed component, or L, G is a conductance. I'll write a same resistor symbol, and C. So high frequency circuit will behave like a distributed elements, because this section will have a different impedance. This is coming in the transmission line. This is maybe 1 centimeter. After going another 1 centimeter, there is again RLGC will vary. So this become a distributed elements, distributed impedance. So no more the impedances will be a constant. Normally, if you take a 2 lines, it is whatever voltage you apply, for example 5 voltage, the same voltage is supposed to get, provided that is a lossless. You take a very superconductor, so 5 voltage you apply, you get a 5 voltage. There is no attenuation in that. But this is at a low frequency. Obviously frequency is low, the wavelength is quite higher, so there is no instantaneous change in the voltage. When signal is started, the wavelength sense, it will end after the physical line of the length get over, it will start here, it may end somewhere. So there won't be any much delay between the transmission and reception. But in a higher frequency, the things getting complicated. You have all our distributed elements here. So each section will have a, because the signal is, wavelength is small, so signal is very small, the wavelength is small, the voltage current is changing between the lines. So what happens, the voltage current is changes, impedance is changing. This impedance is coming from this primary constant of transmission line. That what we have seen in the transmission line. So what, in the simple sentence, in high frequency it is not simple transmission line, so it becomes a distributor line. In the distribution line, if you are sending any signal, we are supposed to receive it in the other end. If the impedance is not matched, the signal will start getting reflected back. So at one input itself there is a two waves, that is input, incident and reflected. So that's the reason we need a two lines in each port for high frequency. That is the reason. So if you take a, for example, I'll take another color, maybe here 2 port. This is a 2 port network. This is have a 1. This is I have a 2, second port. So let us see, take this, the voltage at input port is 1, that is V1, and voltage at output is V2. Okay, let us take the current. This is maybe a different color. This is my current I1. Current coming out of this port, this is I2. Okay. So in case if you want the current directions to be, this is coming out, it's supposed to be a negative. Okay. Or the current can be written in opposite directions. This is vary with the side, which side you are seeing it. Okay. So if you take, for example, current in this direction is coming, it is also coming from everything. Current is going into the port. Here another current is coming here, so I can write it as the positive. Okay, if current is going out, it become a minus. So it doesn't matter here, but only for the explanations, not a matter here. That here the intention is, what is Z11? So Z11 is what is the impedance at port 1. Okay, so why there is a 2 number? Because there is a 2 lines. Here input is there. Again, there can be a possible, it can be reflected, because if the impedance of this port is not matched, you can start reflecting it. So the first number always tell us what is the where output, first port. The second number always tell where is the input. So Z11 is nothing but the voltage at V1 and current at I1. Both voltage and current and same port number 1. Okay, so in case if perfectly matched circuit, okay, there is a voltage, whatever is coming, this, what is the impedance, what you are getting is become an input impedance. Okay, so similarly if you take Z21, so what is the voltage at 2 and what is the current from 1? Okay, what is the voltage as 2, what is the current coming from the first port? So this is what we call is the impedance between 2 and 1. Okay, and another one is at 1. What is the voltage at 1 coming from current from 2? Okay, similarly Z22 is what is the voltage at 2 from the current from port 2. Okay, these are the parameters. So here how I can write Z matrix, Z11, Z12, Z21, Z22. Okay, so in case here this is Z matrix, just straightly written there. So here for example, if you take a first equation, Z11 equal to V1 by I1, okay, is there, but is it always true? That we have to find out from the linear algebraic equation of this 2-port network. So how I can write V equals to Z into I. So this is a V1, V2, this is I1 and I2. Okay, so if you take a V1 is equals to Z11 times of I1 plus Z12 times of I2. Let us take things simple. So I will take only Z11, rest of the things is similar. So we need to find out what is Z11. So Z11 equals to V1 by I1. Can I write V1 by I1? Provided that, this is very important, provided that I2 equals to 0. So what it means, the impedance at first port is equals to the voltage, what are the voltage in the first port, divided by what is the current in the first port, provided that there is no reflected current from the output port. If there is, for example, after second port network, if I connecting some antennas, or let us say some op-amp I am connecting, so any device, let it be op-amp. If op-amp is not matched correctly, there may be a reflection from the op-amp. So that if the reflection, then I2 is not equals to 0. If I2 is equal to not 0, so this is not valid. This equation is not valid. Okay. So how we get this Z parameters? From the linear algebraic equations and ratio of, for easier convention, the first number always will be the output and the second number always will be the input. What is the voltage at 1 and what is the current at 1? That is V by I is Z11. Similarly, if you take Z21, what is the voltage is second port, the current from the first port. Okay, again this is valid only if I take Z21 valid only whenever I2 equal to 0. Okay, so Z12 equal to V1 by I2 provided that whenever I1 equal to 0. Z22 equal to V2 by I2 provided that I1 equal to 0. So these is very important. Whenever this is there, means that other ports are perfectly matched. This is the two port network. If you understand this clearly, so what this is a parameter is doing in the two port, so I can easily expand these concepts to n port device. Okay, so once I know this Z matrix, I can get a blueprint of the device. Okay, this is a general Z matrix. We will see that some parameters based on the Z parameters and similarly Y parameters and try to understand. So what information, useful information I will get it. Obviously what is the usefulness we will find out. We have written already. If I know the Z11, okay, it is something like, if you know the Z11, if you know the current, what is the current, if you know the what is the input voltage you are giving, the current you can easily find out. Okay, if any known quantity is there, you can find out unknown quantity. So if you know the Z parameter, we can find out which is quantity is not known. That is the one applications. Another application is it will tell some information about the device. If the Z parameter, for example, 0 and 0, not 0, let us take this is Z11, this is Z22. If Z12 is there as it is, if you write Z21 equal to Z12, if Z12 equal to Z21 or Z21 equals to Z12, if both are same, then we call this as a symmetry device or reciprocal. Remember this term, it will be useful in the reciprocal, okay, or symmetry device, meaning that I can interchange this device. For example, if two port is symmetry, I can just reverse this device. I can, instead of giving input here, I can give the input here and take output. Okay, I can interchange it so that I can use it at however way I want. It's similar like a resistor connected. Okay, I can resistor, we can connect in different polarity, so it will be the same. So similarly, if it is symmetry, I can use it in any way. So if the symmetry device, if Zij, in general, it will be equal to Zji. Okay, Z12 equal to Z21. So in a matrix form, how we can tell? If Zij equal to Zji, in the matrix form, if you take a matrix, if you take a transpose of matrix, both will be the same. For example, you take this matrix, this is symmetric device. So Z11, Z12, Z21 equals to Z12, that is what symmetric device, and Z22. If you take a transpose of this, write a column into row, okay, and second column into row, so which is nothing but same. So the matrix, Z matrix and transpose of the matrix, both will be same for a symmetric device. This is one property of Z parameter. So another property is, if the Z parameter values, I told it can be a complex number, a plus ib, this a1 plus jib1, a2 plus, like that. It can be a complex number. So this is a rectangular format. Even polar format also I can write r1 theta 1, r2 theta 2, like that. So if it is a lossless, if the complex number is there, and if you don't have any real value, only complex number is there, okay. So for example, if you have only theta 1, theta 2, or if you have only j beta 1, j b1, j b2, if the Z matrix is having only the complex number, not a real number, it is called lossless device. The device will be a lossless, meaning that if you send 1 milliwatts power, no power will be wasted in the 2 port, all the power will be given to the 7 port. Okay, we'll go back to the slides. That what is given in the slides in the N-port device, you can expand the same 2 port concepts to the N-port and you can easily understand. So the same thing only explained here, provided that other currents are 0, then only this equation is valid. Similarly for admittance, you can write I1 by V4, output at 1 port, the current, and input from the 4th port, that is a voltage. I by V is nothing but admittance. The same we can expand Z to Y. So once we know that Z and Y, then we can go to the S parameters, and properties we have already saw that. I think as I mentioned here before, to go to the scattering, I'll just revise it. What are the properties of Z and Y? As I mentioned, if matrix and transpose of the matrix or inverse of the matrix, if it is the same, it is called symmetric device. Okay, and it's something like a resistor. If we take a non-reciprocal, like if you cannot interchange, that is called a non-reciprocal device. For example, diode. Okay, in the low frequency circuit. Anyway, we will see that some of example in the microwave devices where 2-port network is non-reciprocal. So lossless, if the device is lossless, then Z or Y parameter will have only the complex number, that is not a complex exactly, it is a imaginary number, that is JB. It don't have a real value. Okay, so for a more like derivations, no, like how you are saying that, if how you are saying that if it is having only the imaginary number, it's a lossless, how is that? So you can see it more in the derivation in the textbook. It is not directly needed for solving the problems. We can concentrate some practical problems which will be useful for exam and also for a practical reason.